All right, guys. Welcome to today's lesson on what's called intermolecular forces. And you guys think about what that might mean. That word inter, if you guys think international, interstate, what does inter mean? Doesn't it mean between? When you have an interstate highway, that's a highway that goes between different states. International would be like trade between different nations. So this is describing the forces that exist between molecules that hold molecules together. I want you guys to check out this overhead. Okay, guys, check out different substances. For example, here we have propane. It contains carbon and hydrogen. The black are the carbon atoms, and propane's a hydrocarbon. You guys see. You have sugar. Sugar has a bunch of carbons and hydrogens, and then the red are oxygens. You guys remember we said a lot of organic compounds have carbons, hydrogens, and oxygens. Look at gasoline here. Gasoline has just carbons and hydrogens, a long hydrocarbon chain. Here we actually have alcohol, rubbing alcohol. You can see it's got a bunch of carbons, hydrogens, and then it has an oxygen as well. And then this is one. This is actually the most used drug in the world. Maybe you guys could guess the most used drug in the world. We're not talking heroin, cocaine. I didn't say illicit drugs. This is actually aspirin. So aspirin that we use to it's kind of a blood thinner, and it also reduce headaches, things like that. Contains carbons, hydrogens, and oxygens. What you guys will notice is these are all in different states of matter, and it all has to do with how strong their intermolecular forces are. So at room temperature, propane is a gas, sugar is a solid, gasoline is a liquid, rubbing alcohol is a liquid, and aspirin is a solid. What we're going to learn today is what is it that determines the strength of the intermolecular forces, which ultimately determines what phase a substance is in. When you guys imagine the ones that are solids, that would indicate there must be strong intermolecular forces holding the molecules together, whereas with the liquids, they have the forces are less strong, and then the ones that exist as gases like propane, right, where the molecules are kind of independent of one another, you would imagine they have very weak intermolecular forces. So that's what we're looking at today. She says, "This is from Victoria's Secrets. Do you like it?" He says, "They should have kept it a secret. It's kind of messed up." Okay, anyways. So, you guys write this down. You guys remember we talked about first semester covalent bonds. Remember, if these are non-metal atoms, it's going to be covalent bonds that holds them together. Remember, atoms that are going to share electrons between them, and that's what's holding them together is electrons orbit both nuclei. So the question, however, though, is what is it that's holding molecules together? Because remember, if there was nothing holding molecules together, you would expect everything in the universe to just be a gas. All molecules would just be independent of one another. But we do obviously have liquids and solids, indicating there must be something, attractive force, pulling them together. That's what's called an intermolecular force. So the intermolecular force, notice where it's pointing. It's pointing in between. It's what we're talking about holds the whole molecules together. Those are relatively weak forces that bind molecule to molecule. And we say weak because they're only about 1/100th as strong as covalent bonds. Because, for example, what we're saying is think about like a water molecule, right? You got covalent bonds holding the atoms together, and then you have intermolecular forces holding the molecules together, right? And that explains why water is a liquid. It must have a force of attraction holding it together. Well, if you heat up water, so if you add energy, you would not expect to you wouldn't expect to break the bond, the covalent bond between for example, the oxygen and the hydrogen. When you heat up water, because what happens? Obviously, you guys know you heat up water. What happens? It evaporates. When it evaporates, the water molecule itself is not breaking up. What's happening is the molecules are separating, indicating that the intermolecular forces between it is much weaker than the covalent bond holding the atoms together. They're due to the force of attraction of the nuclei of atoms in one molecule for the electrons in the atoms of another molecule and vice versa. You guys remember, that's what atoms consist of, are just pretty much protons and electrons. You notice I'm putting the positive in the center because that's your nucleus that contains your positive protons. So what we're saying here is, not only do electrons have an attraction for the positive nucleus in adjacent atoms within a molecule. But wouldn't you guys agree there's also a weaker attraction that electrons of the atoms of one molecule would have for the positive nuclei of the atoms of adjacent molecules? Okay? So just think about it, you guys. A lot of chemistry just has to do with the attraction of protons and electrons. And you guys, the bond strength, the strength of this is determined by various factors: shape, size, and polarity. We're not going to look at shape so much today as size and polarity. We're going to see how the size of the molecule and whether it's polar or not has a tremendous impact on the strength of those intermolecular forces. Okay, so you guys, let's consider some compounds here. We have, for example, CH4 should be a compound familiar to you guys. Remember, this is methane. Remember, this is the gas that you produce on your stove at home if you have a gas stove. You guys see it's, and then SiH4 and GH4, just so you guys know, where's this? The only difference in these, you guys look, CH4C is right here in your periodic table. Si, silicon, is just below it, and GE is just below it. You guys see they all bind to 4 hydrogen atoms, as you would expect, because they're all in the same column. They all have the same valence electrons. So you would all expect them to have the same shape. And you guys should know what this shape is. You guys remember from first semester? That's called the tetrahedral shape. So they all have a tetrahedral shape, so the shape's the same. Now polarity. You guys remember how you tell polarity? Basically, you look at a molecule and you see if it looks symmetrical or not. I have a center atom. I have 4 hydrogens bound to the center atom. I look and I see, does it look symmetrical? And if you look at your molecule and if it looks symmetrical, it looks the same on both sides, there's a good indication that the electrons are evenly distributed, and therefore it is non-polar. It doesn't have positive and negative sides. The electrons are evenly distributed, so there's no polarity. So all of these are non-polar. So you guys, how do they differ? They're only going to differ by size. Check it out. You guys see how the CH4 are the smallest, because if you guys look on a periodic table, carbons are smaller than silicons, which are smaller than germanium. So this is just kind of showing relative sizes, all right? So now the question is, which would you guys expect to have stronger intermolecular forces holding them together? And so the question is, how do you guys think we could test that? How could we test that? How could we what could we do to them? What do you guys think we could do? What do we do to a lot of substances when we want to kind of analyze it? Don't we heat it up? And so what could we measure? You guys, couldn't we measure the boiling point? The boiling point, you guys know what the boiling point is. It's the temperature at which it goes from a liquid to a gas, right? And when you guys imagine the higher the boiling point, that would indicate the stronger the intermolecular force, because that would indicate the higher the temperature it'd have to reach in order for it to have enough kinetic energy to overcome the intermolecular forces to break up. So at this point, before I show it, I want you guys to kind of put a speculation. Which do you guys think is going to have the highest boiling point, indicating the strongest intermolecular forces? Is it going to be the smallest one, CH4, medium-sized one, SiH4, or the largest one, GH4? You guys look, okay, so what we're going to do is we measure the boiling point. Those are known. We look at, and these are, it can be a little difficult, guys, because you notice they're all negative values. You know what that means? These all boiled off way at very low temperatures. So right now, these are all gases. Just like you guys know, methane's a gas at room temperature. All these are gases at room temperature. But you guys, hopefully you guys can tell which one has the highest boiling point. Notice the negatives. The highest boiling point is this one. You notice this boiled off, this went from a liquid to a gas at 161 degrees below zero. This at 112. This one, not until it was only 90 degrees below zero. And so what we see is the larger ones have higher boiling points. So what does that indicate, guys? They have the higher boiling point. That indicates they have the strongest intermolecular forces, because that means it has to absorb all the more heat in order to separate those molecules. And you guys, the reason why is, if you think about it, the larger the molecule, basically the larger the atoms, what does that indicate, guys? The more electrons they have. Just think about it. The larger the atoms, the more the electrons. Electrons are moving, and they're causing an attraction between the different molecules. So think about it, guys. The more electrons, the more what we call polarizable, and thus the stronger the intermolecular forces. So just realize that, guys. The larger the molecule generally, the stronger the intermolecular forces. Okay, so that was size. Resolutions, new year. Number 1, finish things I start. You guys notice he didn't even finish his list. Not good, not good. Last factor we're going to look at is polarity. So let's look at two compounds. We got carbon tetrachloride. So you guys, this could kind of show carbon tetrachloride. In this case, the carbon's the blue, and the 4 chlorines are the white. And then look at methyl chloride. You guys see the difference is it's a carbon in the middle, and it's got let's say three hydrogens, except the only difference is, let's go with this. Let's say one of them is a chlorine. You guys see that? This would be like methyl chloride, and then this right here is CCl4, okay? So now if you guys look at the shape, if you notice the shape is the same. The shape is the same, so there's no difference in shape, and the shape is tetrahedral. Really the difference is in polarity, okay? Okay, now if you guys look at carbon tetrachloride, you guys look, does it look symmetrical? Is it the same on both sides? Yes, it is. So we would say it's non-polar. But now look at this one. Look at CH3Cl. You guys see one of the outer ones. So these are hydrogens, and this is a chlorine. Is this symmetric? You might think it looks like this, but then all I have to do is do this. You guys look. This has a different atom. In fact, you guys see when you got a chlorine. You guys remember where chlorine's at? You guys have got to remember this. These atoms that are in the upper right, they're very high electronegativity. They have a strong pull on electrons. Whenever you have atoms like that, you're usually going to have a polar compound. So it's polar. So what we see here is the difference between this is nonpolar and this is polar. Okay? So let's look at this. So you guys see the difference is here they're nonpolar, they don't have really, the electrons are evenly distributed. In this case, where you have your highly electronegative atom, that's going to make this side of the molecule more negative and then this side more positive. You guys see it's got an unequal distribution of electrons, okay? So now the question is, which do you expect to have stronger intermolecular forces between the molecules? Would you expect the nonpolar ones or the polar ones? And you remember how we would tell? By measuring the boiling points, okay? You guys think about it, what do you think? And what do we see, guys? Which one has the higher boiling point? And you guys agree it's methyl chloride. So what do we conclude? The polar molecules have stronger intermolecular forces. And you guys, here's why. Check this out. Think about it. When this methyl chloride molecule interacts with another one, how do you think it's going to interact? When you guys agree, the partial negative end of one molecule will have a relatively strong attraction for the partial positive end of the next molecule. You guys see that? And so that makes for an extra strong attraction, or a stronger attraction than you would have between two nonpolar molecules which have equal electron distributions. So you guys, these in actuality are both liquids. This one's not going to boil off until 76 degrees Celsius. I don't know, that's like 150 degrees Fahrenheit, something like that, I can't remember. And then this one not until even later. Okay, one last concept we're going to introduce, guys. Not toilet concept, but dogs. Another resolution down the drain. He had resolved that he wasn't going to drink out of the toilet anymore, but temptation was too great. Okay, just want us to kind of look at something. You guys are going to analyze data like a chemist, like a scientist would. So we have these compounds. Of all these compounds, probably the only one you guys are somewhat familiar with is NH3. You guys remember that's ammonia. Remember that's the main ingredient in Windex. You use it in a lot of cleaners. Well, you guys, there's a lot of similarity in these. They're all bound to 3 hydrogens. Here's the only difference. Nitrogen's here in the nitrogen column, and then under it is phosphorus, under it is arsenic, and under it is antimony. So the center atom is in the same. They're bound to 3 hydrogens. They're all going to have the same shape. So they all have, here, let me show you guys one sec. Oh, here's the shape of those ones. Right, you guys, they have 3 hydrogens, and then you remember they have a lone pair. If you do the Lewis structure, you see that. So they all have the same shape, and then polarity, you guys look, once again, I see, does it look symmetrical or not? It kind of looks symmetrical, but then all I have to do is this, and then you have this lone pair of electrons. It's not symmetrical, uneven distribution of electrons, so they're all polar, okay? So we all have, so they all share a lot of the same, they all have the same polarity, they all have the same shape. The only difference is the size, okay? If you look at the size, it increases as you go up, and that, you guys remember that's why, because remember it was nitrogen, then it was phosphorus, then arsenic, and then antimony. So the center atom here, so the size is increasing. So you guys think about it, based upon what we just discussed, what would we expect to see with the boiling points? If the size increases as you go up, what would we expect to see with the boiling points? When we expect the boiling points to go up? Because remember, the bigger the size, the stronger the intermolecular force because of the more electrons they have to interact with each other. And let's see. So I'm kind of looking, and let's see, does the data fit our prediction based upon our what we just learned? I'm kind of looking at this. Look, it's negative 85. And then when you guys agree negative 55 is higher boiling point than negative 85, and when you agree negative 17 is higher than negative 55, so it seems like it's all working, but doesn't it seem like there's a, what is the enigma? Enigma is something that seems like it doesn't fit. When you guys agree ammonia doesn't fit the scenario, we would have predicted ammonia being the smallest, having the least sized atoms, the least electrons. We would have expected to have the weakest intermolecular forces between its molecules, and thus the lowest boiling point. But what do we recognize? It has one of the highest boiling. Its boiling point would be kind of somewhere up in here. Okay, so that kind of leaves us with a question. This is what scientists would do, guys. We would collect data, and then we'd analyze the data and see does it fit our model. And if it didn't fit our model, then maybe we have to change our model. So let's see. Let's look at one other one, guys. Okay, just stick with me. We're going to look at some. Once again, we see 4 compounds here. The only one that you guys are probably familiar with is water. We're familiar with water, right? Here we got water. Now, you guys, the only difference is the center atom. Rather than oxygen being the center atom, here we have sulfur, selenium, and tellurium. Just so you guys can see on the periodic table, there, once again, the center atom here, they all fit in the same column. Here is sulfur is just under oxygen, and then selenium is just under sulfur, and then tellurium is just under selenium. So, if the center atom, you guys, I know it's kind of the reverse of what we're seeing here, but oxygen, sulfur, selenium, tellurium, the center atom's getting heavier, and thus more electrons. So what we're seeing here is we go up, and the polarity would be the same. You guys, they would all have the same shape. They're all polar. So really, once again, what's the only difference is the size. Okay. And what we see with the size is the size of the compound, the molecule is increasing as you go up. So what would we expect? Remember, the larger the molecule, the heavier the atoms, the more electrons those atoms have, and therefore the more interaction between the electrons of one atom for that of the atoms in an adjacent molecule, and therefore the stronger the intermolecular force, you would expect the higher the boiling point, right? The higher the temperature you have to reach in order to get it to boil. Let's see if that's the case. So we're looking here. Guys, let's see if that's the case. It kind of looks, oh, you guys see I made a typo, right? You guys obviously, what should that be, right? No, silly, I caught you. No, you guys, the boiling point of water is 100 degrees Celsius. You guys should remember that. It's really easy. In fact, that's how they set up the Celsius scale, was based upon when, you guys know, water freezes at 0 degrees Celsius. Really easy to remember. Water boils at 100 degrees Celsius. Now, you guys, this should kind of be like, what? What's going on here? This is the smallest molecule. Now, check it out. Let's look at the other ones. We go, right? The size of the molecule is getting bigger, and so as expected, look, the boiling point is increasing. Yet water, which is the smallest molecule, because oxygen is very small compared to sulfur, selenium, and tellurium, yet it has by far the highest boiling point. It has a boiling point of 100 degrees Celsius. And you guys, it's a good thing that water has such a high boiling point, because that means water is a what at room temperature? It's not a gas, because it hasn't boiled off yet. You have to reach 100 degrees before it's going to boil off. That's a good thing, guys. It's a good thing that water is a liquid at room temp. Otherwise, you guys, if we're thirsty, we're running, we'd have to. That's my way of like collecting water from the water vapor that's in the air. No, fortunately, water is in the liquid form at room temperature, which allows us to drink much easier. Okay, so we're going to finish today with what might explain this. What explains why these small molecules like water, and you guys remember the other one was ammonia, both which are smaller molecules, we would have expected them to have the lowest boiling point, but in actuality they have some of the highest boiling points. What that means is there is a stronger attraction between those molecules, they have stronger intermolecular forces than you would otherwise expect, because due to the fact that they're so small. So, for example, you guys look, these are like some, check these ones out right here. Like these are some major components of air. You guys know the number one component of air is nitrogen, N2. The next biggest component is oxygen, O2, and then the next would be CO2, and then you also have hydrogen. And then you also know And then you notice, what do you guys notice about the molecules that make up the mixture of air? Don't you realize they're all small molecules? Look, 2 atoms, 2 atoms, 3 atoms, 2 atoms, they're all small molecules. And you guys, that's not surprising. What do we say? The smaller the molecule, the less heavy the atoms, or the less electrons, and then thus the weaker the force of attraction, and therefore it's not surprising that with weak intermolecular forces would be gas at room temp. Yet what do we find? Water. You guys, water is H2O. Look, this is a small molecule, H2O, and yet what do you notice? It's a liquid at room temp. What would explain that? What explains why it has a stronger intermolecular force? It's this right here, guys. It's called a hydrogen bond. Last concept, guys. Stick with me. Let's see where we're at on time. Okay. So a hydrogen bond is an extra strong bond, about 10 times stronger than you would expect it to be. What do you guys think about it? There's 2 prerequisites to have a hydrogen bond. So you guys are going to have to be able to predict when a hydrogen bond could occur between molecules. Well, gee, what do you guys think? It's called a hydrogen bond. What do you guys think might be a prerequisite? The molecule must contain, you guessed it, hydrogen atoms. And then there's one other prerequisite. Now you guys look at the 2 examples that we showed. So think about it. See, you guys see water meets that. Requirement. It's got hydrogen. And then look at the other one. You remember the other one was ammonia that had an extra high boiling point. So then think about it. If we're using ammonia and water as our examples, what might be the other requirement? Kind of want you at this point to pause it and think, okay, what would be the other requirement besides having hydrogen atoms? Has to have hydrogen atoms, and then some of you guys might have guessed it. The other, it also has to have an atom that has a highly electronegative atom. And in particular, it's got to be nitrogen, oxygen, and fluorine. You know what's key about it? You know where you guys will find nitrogen, oxygen, and fluorine? You guessed it, in the upper right. You guys remember? Very electronegative. So if you have a very electronegative atom, nitrogen, oxygen, and fluorine, and it's bound to a hydrogen atom, there's a good chance you could predict that it's going to exhibit hydrogen bonding, and therefore it's going to be holding together a lot more strongly than you would otherwise anticipate. You guys, here's the reason why. Think about it. Almost done here, guys. Normally, look at water. Very small molecule, we'd expect it to be a gas at room temp. Good thing it's not. That's why we're able to survive as humans, right? Drink water. So, think about, here's why it makes it extremely strong. Okay, we have oxygen here and hydrogen here. You guys think about, what is a hydrogen atom? If you look on your periodic table, a hydrogen atom is just a proton and an electron. You notice it doesn't even have a neutron. So it's the smallest, simplest atom. And then think about it. There's a covalent bond here indicating the one hydrogen atom, electron, is being shared with the oxygen atom. Remember, this is sharing a pair of electrons. And where's that pair of electrons? Because this is highly electronegative, where's that pair of electrons spending most of its time? Around the oxygen atom. So what does that essentially leave here? Well, if a hydrogen is just a proton and electron, and its electron is primarily by the hydrogen, the oxygen, isn't it primarily just a proton? It's like a naked proton. Now think about it, guys. You kind of have these kind of naked protons here, and think about another adjacent water molecule. Once again, you guys, we have a naked proton, which makes this like very partially positive. And then, you guys, you think about what's that going to be attracted to in an adjacent water molecule. Think about, not only do you have this electronegative atom, you have this lone pair of electrons, these naked electrons. So essentially you have a naked proton and a naked electron. This is almost like chemical pornography, guys. It's kind of disgusting. It's a very strong attraction between those types of molecules. Once again, what's necessary? A very electronegative atom bound to hydrogens. If you have that, it's an extremely strong interaction, which would explain why, for example, water, which normally you expect to be a gas, is actually a liquid at room temperature. All right, guys, thanks for joining me. See you next time.